Hello everyone, it is with great pleasure that I'm presenting this talk today in the CP 2021. The focus of my talk will be on the fatigue failure transition analysis of load-carrying cruciform welded joint by extended local approach. I'd like to acknowledge the support of the founding of a fundamental agency and the industry partners. This particular presentation is to analyze the basic fatigue properties of a high-strength steel welded joints, consider the misalignment effect. But as part of a large project of design analysis as well as manufactured ship and submarine welded components. So the outline of the research will be divided into five parts. The first one is about the presentation, the motivation. Uh, the motivation about the research. One of the effective way to enhance the light weight of structures is to increase the strength of the steel for decreases. This study aimed at investigating the fatigue property of difference between the base metal and the welded metal, and the second aims is about the low cycle fatigue life of mismatched welded joint. The third is about the fatigue life prediction models, about the uh, fatigue failure transition curves of the uh, load carrying cruciform joint. So the possible application of this study in the future uh, is uh, uh, is uh, is about the geometry optimization of RCWG, considering the material property and the geometry uh, sizes. The second application is about to improve the fatigue life prediction of the RCWG and the and the uh, accurate predict the fatigue failure uh, locations by the effective notch uh, energy method for the welded tool or welded rule failure in RCWG. So this is about the material properties. We used the high strength steel and the under mismatched welded is was used to welded the RCWG. So the property of about the yield strength, cyclic yield strength, and the tensile strength strength is represented in this table, and the experimental details about the test about the RCWG were presented like this, and we cut the specimen from the cruciform jointed plane, and their fatigue test were conducted by the Armstrong and MTS fatigue machine. So the specimen details and the fatigue test details were presented are presented in this page. And according to the experimental specimens, we established different the filament analysis models according to the sizes of the specimen. In this picture, we can see the different material zones in this picture and mesh size about this model. According to the result of the fatigue failure location from the fatigue test, we can see the different potential failure locations can be observed from the picture. Some specimen is were failure from the root, and some other specimens are failure from the welded tool. So it depends on different um, on the loading levels. So we need to analyze the failure location according to the loading conditions. Thus, it is because we choose the different machines and the different the sizes to analyze these specimens. Generally, the effective notch strength can be used to present the low cycle fatigue properties of the welded joints. So we use this fatigue indicator to present the variations of the notch strength according to the variation of the penetration ratio and the weld length and the mismatch ratio, mismatch effect. So we can see from this picture the variations of notch strength distribution, and according um, uh, the equation of the effective notch energy, we established the uh, analytical solution models from uh, based on the effective notch energy method. So we established this model like this. This figure shows the energy concentration factor according to the analytical solution models, considering the mismatch ratio effect and the penetration ratio effect. And from this result, we can conclude that the material mismatch and the geometry effects on word root and the word tool of RCWG are significant on the notch concentration factor according to the analytical solution models. Based on the models, we compared the results of plastic concentration factor between the FEA and the analytical solution models. From this result, we can see that it has good agreement between FEA and analytical solutions. On the basis of the analytical solution models, we can get the 3D contours about the welded tool and the welded rule failures. So by comparison, these contours, we can conclude the transition curves between these failure positions. Considering the mismatch ratio and the geometrical effects, the uh, the fatigue failure transition curves are compared in this figure. So we can see there's a good agreement between the elastic and the elastoplastic regimes calculations. So we compared the transition curves considering the mismatch ratio and the different failure locations. Thus, the notch effective concentration factors comparison of different mismatch ratios and penetration length ratios and welded length ratios, and some comparison of transition curves between welded and welded tool on the different mismatch are compared. These predicted curves can be used to predict the failure location. Finally, the conclusions can be drawn like as follows. The first one is that an analytical model is established to characterize the effective notch energy in elastic plastic mechanical regime, representing the combined effects of these vectors. And the second is that the notch energy estimations of RCWG from the model are in good agreement with the magnitude by the elasto and the plastic FEM results. In terms of the energy life curves, it can be effective to access the fatigue strength of RCWGs in HCF and LCF regimes. The third is that the quantitative relationships of the fatigue failure transition were determined considering the yield strength mismatch and the geometry factors. Thanks for your attention.